Welcome back, class, to the Verilog session on registers and register files. So first we'll design the register. The n-bit register is shown in the screen, and we'll build a Verilog model for this n-bit register. So first of all, register contains, so this is a register that contains n bits that can be read out at the at a positive edge of the clock cycle, and any data that has to be written inside the register is input using this data underscore in port, and it has an n-bit port, and if the write signal is on, so then this data underscore in gets written into the register. The other inputs are the reset input, and when the reset input is applied, right, the register is cleared. Right, let's keep that as the behavior, and the clock, of course, which is constant to all sequential circuits. So what we will code in as behavior of the register is put in this slide. First of all, well, you can output the data of the register in two different ways. One is a sequential, that is only when the passage happens, then you output data underscore out. That is one way of doing it. The way I will do it and show in this lecture is that it outputs combinationally the data underscore out. So whenever data is written into the register, that is sort of combinationally drawn out of the register and put at the output. That will be the behavior of the data underscore out. The data underscore in, however, the write is happening at the passage. Right, so let me just mark this. This is one way of doing it. What I'm doing is the other way of doing this. This is sort of combinational data out, whereas the write is sequential. That is, the write happens only at passage, right at the passage of the clock, and when the write signal is turned on. So when if this is the clock, right, when the clock meets the right edge, so meets the positive edge, the write has to be on at this point. So if this is the write signal, the write has to be on. That will be the behavior. The other thing is reset, right? So when reset is 1, or when reset transitions to 1, we will clear the register. So the register contents will be equal to, say, 0, whatever the other contents it must have had before. So the register contents will be equal, say, let the register was 1, after the reset the register will be 0. Right. Let's code in this behavior. So first I will show the code in the slides, and later we can code it up in Verilog. This is the, of course, this is the module. This is the picture of the module is already shown. This the advantage of writing the block diagram in this manner is we now know all the inputs and the output of this register. So this is the input is data in, which is an n-bit input, and reset is a single bit, clock is a 1 bit, and write is a 1 bit command input, and data out is also the n-bit output. And the definition of the module definition of the register is shown over here. We've written reg n to say that n-bit register, and we can sort of make n configurable. And to make n configurable, we use this constant definition called parameter, and in this case I put 1 byte register, which is 8 bits of register, and the input in you can observe the same n being used in the data input and the data output declarations, where basically we are saying this is now going to be a 7:0 register, right? And you can have this n configurable now. These two lines are declaring clock, reset, and write, and the register itself, right? This is the element itself. This is the memory element itself, which is again n bits large, with 7, which is the MSB, and 0 being the LSB. We will first write the reset behavior. This is an asynchronous reset. So this is I should have written it here, right? This is an asynchronous reset, meaning anytime during the clock reset can be 1. This is being the clock, right? This being clock. Anytime at any time period, if the reset is applied here, so the reset is applied here, and the register value inside the register, if it is high, it becomes low. If it is low, it stays low. So this is the clearing of the register. So this is let me say There is an 8-bit register, so all of this will become 0 0. Yeah, 8 bits of 0. It could have any value here before the reset was applied. Right? It could have any value before the reset. That's what is being also coded in here. Whenever reset changes, if reset is 1 or reset has changed to 1, then basically clear the register. So this does clearing of the register. The next is the write behavior. For the write behavior, we already mentioned that it is going to be sequential. So at the passage of the clock, when the clock transitions to 1, if there is a write signal that is on, right? So if the write signal is on at this point, write can happen. So the register gets the value fed in from data in at the passage of the clock. So that is the write behavior. The next is the read behavior. So read behavior in this Verilog model, we are sort of writing it out as the combinational output of the register. So that means that it does not wait for the passage of the clock, or it does not wait for the clock as a trigger. So any data that is present in the register is continuously being read out using this data underscore out output interface. Right. There could be other ways of coding this. You could do this at passage. This is right now combinational output, right? So you could do this at sequential readout data out at the positive edge of the clock. But what is shown here is actually the combinational output of the data out. So we will code up this register now. So the test bench for this single register, basically what we will do is consecutively write random data in successive cycles and read the data that has just been written inside the register, just to test if the register is working correctly. Of course, we'll also test the reset input to the register. I am not showing the full test bench. The rest of the parts can be filled in while we are writing the code itself. So, but of course, you can see that this is the reset block where wait for one time unit and then make reset as 1, and then wait for one more time unit. So the reset is on for say 1 time unit, and that's it. The write was initially equal to 0 as an initialization step. This is the reset block, the reset initial block. Reset block. The other block shown here is the read and write behavior. This is basically the read and write behavior. So write and read behavior. So I just write and read block. So what this read write block is trying to do is to write at when a positive edge arrives, right? So make the write signal 1 when a positive edge arrives, and give some data input which is written into the register immediately at the positive edge, and then wait for one more clock cycle before writing one more piece of data. And in that one clock cycle where write equals 0 here, so basically the data can be read out and completely observe, when we can observe what the data is inside the register. So let me show it with the clock cycle. So the clock is not shown on this screen, however the clock period is 20 time units. So this is 20 time units, and during this 20 time units, so the write signal is turned on for one positive edge, and the write sort of completes here. Along with the write signal, also the data in signal, a new data in is also sort of fed to the register, and the successive next positive edge, nothing happens. That is, write is not on. The write becomes on before the positive edge after that. So so this clock cycle is fully available for us to sort of read and observe the contents of the register file. So this is when read can happen. Of course, the read that we have done in the Verilog is a asynchronous read. So the new value of the data will be available immediately after the write is happening. That is, it will be available immediately here. So basically, the test bench once in 2 clock cycles writes a new value inside the register. Right. So let's code this up now. There are different ways of doing this. You can do it in many different ways, but this is the approach that I have taken. So let's code the register in Verilog. So this is the n-bit register, and of course, let me just write out the input. So input is data in, and of course, which is n-bit data in. Then we have the reset, the clock, and the write command. Output, it has only one output, which is the n-bit data output, and that is sort of combination. So start off with the module. So yeah, module, call it reg, and very similar to what is there in the slides. Module, and say data out, data in, the write command, reset, and the clock. Input n-bit, yeah, so n-bit data in, and the n will make configurable. So we'll put a parameter n, which is equal to, say for example, now it is 8. So it is n minus 1 to 0 is data in. So similarly, data out will also be that, and this is output. So another input is the write command, then there is the reset and the clock input. Then of course there is the register itself, which is again the n-bit register, call it register. Now what I will do first is the reset behavior. So then we'll do the write behavior and basically the read. The reset behavior is that always it resets, so that whenever anything happens to the reset, then we will say if the reset is becoming 1, then the register is equal to 0. Of course, here it is 8 bits, I just write 0. So the write behavior is always at the pause edge of the clock. At the pause edge of the clock, if of course there is no reset, and if the write command is on, then the register should contain data in. Note the non-blocking assignment at pause edge, always it's suggested, and the synthesis tools also sort of interpret for the synthesis tools to interpret this as flops or as memories. The non-blocking statement, the non-blocking assignment should be used for all positive edge sequential behavior. That's one of the standard practices in Verilog. So that's why I register non-blocking assignment and then data in. The read behavior, we have said that the read behavior will write non-sequential right now. So it's fairly straightforward. Aside data out equals whatever is there in the register. Right. So this is that's for the register, and let's do the test bench directly now. So test bench for n-bit register. So we'll call it register ins test bench. I'm modifying in the first level. Give me a moment. So write this back and save this as reg8 test bench.v. Yeah. Now we can do test bench for and regins test bench, and none of this is required. The rest of the stuff is the same. Inputs are all regs. The output is a wire. Register here, and none of the rest of the stuff is not required. So let's instantiate this, and to instantiate we'll just use the module. Yeah, to instantiate we will use the module declaration from the original DUT. So this is a regen, call it register. First let me do reset, feed reset, then what I want to do is basically write in one cycle, read in the next, and basically repeat this. Right, that's what I want to do. So doing feed reset initial begin end, and we'll start from reset equals 0, wait for a clock cycle, reset equal to 1, and then reset equal to 0 again after another time period. So this is reset, and of course then I will do the clock also. Clock initially clock is 0, then maybe wait for 10 time units, make clock as clock, and that's it. That's for the clock, and I do this for right. I'll also put the save after 300. Finish command here. Now we will do the read write behavior. Note that the clock period is 20 units, so it remains low for 10 time units and then high for another 10 time units, and starts from clock low, so clock high will appear after 10 time units. So that's something that you keep in mind as always. At pause edge, no, what I want to do is the write behavior, right? So write equals 0 initially, so when the simulation begins, write is 0. Let's say after 5 this thing will make write equal to 1, and this has to stay at least for another time, because another 10 time units. Why that is because pause edge arrives at 10, right? So we made it at 1 equal to as 5, so it should stay on till 15 time units, right? So at least that much is right. And okay, so at the same time when write equals 1, we'll also put some value inside data, and we'll make that equal to, say, random for now. Whatever is generated, let it just go inside random. Data is actually 8-bit number, so 8-bit number, so it makes sense to make mod 56. Random, I believe, is a 32-bit number. So write stays 1 for 10 time units, so that's it. So this will write continuously. How many times? So let's repeat it for 10 times. Repeat 10 times to this. So this is happening 10 times, and so we will also read out the value. How I could do that is, after 10 time units I will say make write equals 0, and then wait for 1 clock cycle. That's when, say, we can read out the value, or the data out will be stable, and we can sort of observe what's happening in the data out. So just leave it as. So stays high, write stays high for 10 time units, and then stays low for another 20, then goes back here. So let's see how this sort of works out. I would like to see the GTK wave output of this. Um, so I'll do GTK wave dump whereas from this uh, module dump into a file called reg8.vct. This should be enough. I could do a monitor. Um, right amount. First of all, print the time, and after the time, what is available. Maybe I print data in. Then, if it's data in, then write should make sense. Then, data out, and yeah, I think that's enough. Assuming that the reset and the clock are done correctly. Data in, right signal, data out. Also, let's print the clock. So print the clock first. At time this clock that goes so many bits, right? So let's see if this is. Let's see if this works. So what I wrote just now is reg 8, yeah, it's there, and let's do Verilog reg 8.v and reg 8 underscore t.v. Well, okay, so bpp okay, something is up. So the VCD file is also generated. So let me just open up the GTK wave now. You can also observe the correct output from this from the screen itself. For example, in line say at time 145, right? So let me point it from the mouse. 145. If you look at 145, there is a new value at data n. Previously it was 63 this is hexadecimal 63. At 145 the new value is 0d and the write is made as 1. The data out is 63 from the previous value that is there inside the register. When the clock is equal to 1, that is when the positive edge occurs at 150, so this is still the data in and the write signal. The write signal is still 1 and the data in is 0d, and that gets clocked in to the register, right? So that's what the register stores now, because that's the at the pos edge. And once the register stores the incoming 0d, the same data 0d is present at the output now, right? So the positive edge is at 150 and the negative edge happens at 160. So nothing changes between the positive and the negative edge except that the write becomes 0, and that's why this line is printed at 155. At the negative edge also nothing changes except for the clock value. Then the next clock value becomes 1. Again, the write also has not become 1, and when the write becomes 1 is at 180, that is after 10 clock cycles after the positive edge happens, and this is the next write data, right? So here what is happening is the write has become 0. So this is let's look at it in GTK wave and better understand what's happening, and maybe there is a change for the test bench to be done here. Yeah. So let me just do it with GTK wave now. Okay. So what I wanted really was that before we look at the results itself, what I wanted was the right signal to be on at the positive edge of the clock cycle. So this is good. So as you can see, let me just zoom in if it's possible. So okay, so at the positive edge the right signal is on. This is the right signal, right? So the positive edge is here and it is on. Maybe put it right below. Right, what was required was the right signal arriving at every other passage. So the first passage seems okay, but the next passage, by the time the passage is arriving, the right signal is down. So I'll change the test bench a little bit. So what's happening is, inside one loop the total time unit spent is 35, whereas the clock cycle is 40. So clock cycle is 20 time units. So the time, if I want the right signal to be equal to 1 at every arriving passage, so the delay inside the loop should be equal to 40 time units. So let me do this, right? So we'll wait 5 time units outside only first, right? And make, yeah, immediately right equals 1, and then keep it on for 10 clock cycles, and then say wait until the next passage arrives. So that is wait for another 40 time units here. So the total delay inside the loop be 40. So maybe this will work. So let's see if this works now. I will log that out in GTK. um so at every other passage, yeah, you see the right signal being on, and so at reset, what happens? All the register value becomes equal to 0. Let's see if I can zoom in. So and so the first passage, right? So data in equals 24 in hex, and right signal equal to 1. So that gets written in the as you can see, it gets written at the passage, and immediately that is also presented at the data out. Similarly, the next value, so this 24, the hex 24 stays constant for 2 clock cycles. That is 1 full clock cycle here, and up to the next write happens, and the next write happens at the 2 passages later, right? And the next write is 8-1 in hex, and that 8-1 is ready 5 time units ahead of the positive edge coming, and the write signal also gets turned on, sort of 5 time units before the passage arrives. So 8-1 is ready here, so that data in is ready here, and the write signal is ready here, stays stable until the passage happens. That value is written into the register and is immediately written out or read out from the register, from the data out signal here.